This is a video to go through each of the first three quizzes. We'll go through them in order, 15 questions, chapters 1 through 3. So we'll do quiz 1 first on chapter 1 stuff. Maybe. There we go. So question 1 looks like it is propagation of significant figures through different operations. In this case, the operations are multiplication and then addition. So you had two samples, and you want to report their combined surface area. Sample 1 has a length of 2.1 centimeters and a width of 10 centimeters. Sample 2 has a length of 5.5 centimeters and a width of 3.2 centimeters. And the question is, how should you report the combined area of both? Area is, in this case, length times width. So sample 1 would be 2.1 centimeters times 10 centimeters. Each of those we can assume is two significant digits. In the propagation of significant figures through the operation of multiplication, your result should keep the fewest number of significant figures of the two inputs. In this case, they both have 2, so our report would be reported to 2 significant figures. All right. For object 2, we had a length of 5.5 and a width of 3.2 centimeters. So we multiply that, we get 17.6 square centimeters. But due to the rules of propagation of significant figures, we would keep the 7 as the significant digit. We don't round at intermediate steps. So when we then go to, say, A1 plus A2, that would be 21 square centimeters plus 17.6 square centimeters, but we've underlined the digits that should be significant based on the previous set of operations. The rule for propagation of significant figures through addition or subtraction is that you should keep the decimal place associated with the decimal place that is the largest, that is the significant figure decimal place in either of your inputs or any of your inputs. In this case, the significant figures in both cases happen to be in the ones place, so we would report our answer to the ones place, meaning 38.6 square centimeters should be reported as 39 square centimeters. Question 2. Which of the following choices unambiguously reports a value to the least number of significant digits? 20.0, there's only one reason to include that trailing 0, and that's that it is significant, so that would have 3 significant figures. Same thing with 2.00 times 10 to the first. You would only include those 2 additional zeros if they were significant. They are not placeholders, for example. So that would be 3 significant figures. 2 times 10 to the first, there's only one significant digit there, just 2. 20 is ambiguous, hence unambiguously. That could be either 1 or 2 significant figures. Since the 0, we cannot be sure if it was included because it's significant or because you need a placeholder when you write numbers in this fashion, because the 2 is in the tens place. 20.00 that has, and that's wrong. Should have 4 significant figures. I don't know why I wrote 2 there. Probably have to correct that. So the answer there was, of course, 2 times 10 to the first. Question 3. Density is reported as a comparison of an object's mass and volume. A given object is found to have a weight of 1 pound, takes up a volume of 1 cubic foot. We then have a conversion factor that tells us that on Earth, 1 pound, which is technically a weight, happens to be equivalent to an object that has 454 grams of mass. So we're using weight here, pounds and weight, as if it's a mass through conversion. And 1 foot, which is a measure of length, is equal to 30.5 centimeters, which is also a measure of length. So that's cleaner. Report the density of our object to 2 significant figures. Well, they told us that density is a mass divided by a weight. So mass divided by weight, 1 pound divided by 1 cubic foot. I don't want pounds per cubic foot. I want grams per centimeter cubed. 454 grams is 1 pound, so this is tantamount to multiplying by 1, which you can always do. The benefit of this conversion factor, which you would have learned in chapter 1, is that it will eliminate pounds. Pounds over pounds cancels, and I'm left with grams, the unit I want. A second conversion factor then gets rid of cubic feet in the denominator by placing it in the numerator of my conversion factor that says 1 foot is equal to 35.5 centimeters. And I'll be left with centimeters in the denominator, and we cube that because we have centimeters cubed and foot cubed. So foot cubed cancels with foot cubed. And the answer I'm left with is in units of grams per centimeter cubed, and to two significant figures, that would be 0.0, that's a placeholder, 16, two significant figures. Question 4. In question 5, we find the average values, so I'm just going to report them here. If you take all of these numbers, these 5 numbers for instrument A, and get an average number, your average value from instrument A was 12.03 units. Your average value from instrument B was 11.75 units for this series of measurements in this question. So then what you can do if you want to get an idea of how precise your measurements are is for every measurement, you calculate the difference between the measured value and the average value established by the whole set. So in this case, it would be 12.05 minus 12.03 plus 2 is the variance between the measured value and the average value. So you can get these variance numbers for everyone. And what you'll notice is for instrument A, this variance ranges from plus 0.06 to minus 0.06. Instrument B do the same thing, except its average is 11.75. So the first one is 11.55 minus 11.75 would give you a variance of negative 0.2. And you see for this set, you get a wider spread. You go from negative 0.2 to positive 0.2. So treating this kind of loosely, you all learned how to make absolute uncertainty calculations. Realistically, proper statistics is you'd usually use standard deviations to get standard errors, statistical treatment. But in this case, either way you treat it, what you're going to find is this is clearly the tighter grouping. So conceptually, data that's grouped more tightly for the same measurement made repeatedly is more precise than data with a wider spread. So instrument A is a more precise instrument. Accuracy isn't about your precision of your instrument. So it's not how close each of your reported values come to each other. Instead, it's how close does the average value that the equipment reports come to the actual value. And in this case, we were told that the actual value should be 11.75 units. And if you just look at the averages from each instrument, instrument A returns an average value of 12.03. Instrument B returns an average value of 11.75. So even though instrument B was not as precise, it was clearly better calibrated so that when you took a series of measurements, if you take enough, you get an average value that in this case is equal to the actual value. Quiz 2. All right, so the first question had to do with graphical analysis and it had 5 parts. So this is a skill that you had quite a bit in the Realize It material. It's an important skill, learning objective for this class. So the idea was a matching game where you have 5 graphs on the left, and the question is, and one of them being a motion diagram, which then of the 5 kinematic graphs on the right show the exact same motion, just plotted differently. We'll do this one by one. In graph 1, you have a graph of position versus time, and it has kind of this curved shape to it and eventually becomes flat and constant, meaning it has an unchanging position from this point forward. Unchanging position means velocity should be 0 in this time period, for example. So what we can do, we look at our possible answer choices. They're either position versus time, velocity versus time, or acceleration versus time. Well, this is position versus time. So unless these 2 graphs look identical to that, which they don't, then they can't be the same motion. So these 2 are out for question 1. Velocity versus time. Well, velocity is the slope of a position versus time graph at any point. So at the beginning, our slope is downhill. We start out going downhill. And at the beginning, the hill is steep. And as we continue in time, the hill gets less steep. So steepest, less steep, flat. A flat slope means a slope of 0. A steep downward slope is a negative value. The steeper, the larger the magnitude of that negative value, meaning the more negative it is. So the velocity versus time graph should look like something that starts with a large negative value that gradually becomes closer to 0, reaches 0, and then remains constant. So graph B on the right, velocity versus time, corresponds to graph 1 on the left, position versus time. Uh, Graph, or I should say diagram 2, is a motion diagram that shows an object moving along an x-axis to the left. By convention, we're going to say left is the negative direction. And as time progresses, the object displaces further and further. So this first displacement has a relatively small magnitude. Second step is a larger magnitude. Third step is an even larger magnitude. So this is something that has increasing displacement with time to the left, left being the negative direction. That means this object should have a velocity that is always negative, and that negative velocity should be getting larger in magnitude with time. If we look position versus time, we do not see a position graph that across the full time period is only decreasing, meaning becoming more negative. This becomes more negative than positive. That's not what this did. This actually becomes increasingly positive the whole time. Again, this is only moving left. It should do the opposite. So those two are again out. Velocity versus time. Well, our velocity should always be negative, and it should be increasingly more negative as we go. This starts out negative but becomes increasingly positive, so B is out. So now we're left with one of the two acceleration graphs. What we know from this is that our negative velocity should be getting larger in time. And what that means is we should have a negative acceleration. And that is indeed what we have in graph A. So graph A is consistent with motion diagram B. Graph 3 shows an acceleration where you have an initial time period of constant negative acceleration, and then abruptly at some time halfway through the period, that changes to a positive constant acceleration. Since acceleration is the rate of change of velocity with time, that means in a velocity versus time graph, my acceleration value would tell you my slope. So for the first time period, I would expect to have a constant negative slope in a velocity versus time graph, meaning something that looks like this. And then that would immediately jump to become a positive constant slope of about the same steepness at this break point. I only have one velocity versus time graph. It does not do that. So since my acceleration graphs also don't look just like that, they're out too. So the first three options up here are all not matches to this. So I'm left with these two position versus time graphs. If I have a velocity graph, which would in fact look like this, but this is position, then I would expect that if the velocity is becoming increasingly more negative for the first part of the time and then increasingly more positive for the second period of time, then what that means is I should have a slope in my position versus time graph that's becoming initially increasingly more negative, or that would be tantamount to less positive, followed by, after a breakpoint, a slope that becomes increasingly more positive, which is tantamount to saying less negative. So if we look at our position versus time graphs, this has a constant slope and then another constant slope. That's not a changing slope. That's not consistent with graph 3. By process of elimination, we're left with this graph, but let's make sure it makes sense. In the beginning, we have a steep upward slope. As time progresses, that upward slope becomes closer and closer to flat. That is a decreasing positive slope. That's consistent with a negative acceleration. At the break point, we see that switches to being initially a flat slope that becomes increasingly steeper. That's consistent with a velocity that is starting at zero and becoming increasingly more positive. That's consistent with a constant positive acceleration. So graph E is consistent with graph 3. Graph 4, we begin with a negative velocity that increases at a constant rate of change. Since acceleration is the slope of a velocity versus time graph, this means I should have a constant positive acceleration. That is what graph 3 is, or graph C. So graph 4 and graph C are corresponding to each other. Finally, graph 5 shows a velocity versus time graph, just like the acceleration versus time graph up here. Since velocity is the slope of a position versus time graph, this means I should initially have a negative slope for the beginning time period, and then at the break point, that should abruptly change to become a positive slope. Graph D, position versus time. I initially start with a negative slope that's constant, break point, positive slope that's constant. So graph 5 corresponds to graph D. That's all of the matching. Question 2, more graphical analysis, but now we're putting it together with kinematic definitions a little bit more. So this one says, use the following velocity versus time graph to determine when the object will be traveling the fastest, i.e. with the greatest speed. So this is a velocity versus time graph. Speed is the magnitude of velocity. That means speed will be greatest when my value of velocity is furthest from the value of zero. That is clearly happening here. This is when the graph is furthest from zero at position B. So at position B, the object is traveling with the greatest speed. Okay, same graph, but now we're trying to figure out when the object will have the greatest displacement relative to its initial position at time zero. So whatever position it had at this time. Velocity has signs. That's because it's a vector. Positive means one direction, negative means the other direction. So long as my velocity is positive, I should be continuing to displace in the same direction. So as I go from 0 to A, that whole time I had positive velocity. That means I had a positive displacement. From A to B, I continue to have positive velocity. That means I continue to displace further in that direction. From B to C, I also continue to have continuously positive velocity. I'm slowing down, but still moving in the same direction, which means I continue to displace further in the positive direction. From C to D, that whole time period, I still also have a positive velocity until the very end at point D, where the velocity is instantaneously zero. So that means the whole time from the initial position to point D, I was traveling in the same direction, which means up until this point, D is the furthest I would ever be away from where I started. Now, after point D, we start traveling in the opposite direction. So we have to ask ourselves if by point E, would we have traveled back past our original position and then even further away than what we were at point D? And a way you can estimate that is by calculating the area bounded by the curve and zero. And this area here by eyeball is clearly bigger than this area here, which means we would not even be back to our original position by the time we got to position E, which again then means that position D was indeed the furthest we ever were from where we started, which means that's the greatest magnitude of displacement. Question 4, frog jumps 2.5 meters upward from ground level. How much time will the frog spend airborne? Which means how much time passes between the frog leaving and returning to the ground. Answer to 2 significant digits. So we have to extract information that's both explicitly given and implicitly known. Explicitly, we were told that the displacement of the frog during the upward portion of its journey from ground level to the highest point it will ever reach is 2.5 meters. Implicitly, we know that this frog is in free fall. And when you are in free fall on Earth, that's an assumption to a lot of these questions, you will have a constant downward acceleration equal to negative g, where g is 9.8 meters per second squared. The other thing you implicitly know is when you reach the maximum height during free fall of a free fall trajectory, you necessarily have an instantaneous velocity of 0 meters per second at that time. And let me rephrase that. You necessarily have a y component of your velocity that will be 0 meters per second at that time. And that's because before that point in time, you will be traveling upward, positive velocity. After that point in time, you're traveling negative velocity. You must have come to a stop between changing directions. So these are things we know, one of them explicitly given, two implicitly known. It's these implicit ones that you want to get good at when you're preparing for a test. So once I know these things, I can look at the equations at the top of my quiz and identify the condition. In the y component of my motion, which is everything I hear is y component values, I know I travel with a constant acceleration. In fact, I've already used that to identify what that is. So I'll be looking in my constant acceleration equations. There's three of them. And I ask myself, what could I learn that'll help me get what I want? I want to find the total amount of time before I hit the ground. I don't know how I'm going to get there, but I do see a way to calculate the amount of time it took for the frag to go from the ground to the maximum height. And anytime you're in free fall, if you have equivalent displacements up and down, uh, then necessarily the time period going up will equal the time period going down. So will the change in velocity, as you will see in the next question. So we can calculate the time period associated with going up by simply first two steps. Definition of acceleration could be used to find that, but we'd have to know the change in velocity of the frog on the way up to use it, meaning acceleration is defined by a change in velocity over a change in time. We don't yet know the change in velocity because we don't know the initial upward component of velocity of the frog. But if we look at our other equations on your quiz, we see one that says for something traveling with constant acceleration, the final velocity squared is equal to the initial velocity squared plus twice the constant acceleration multiplied by whatever the displacement is during that time period. We can rearrange that to solve for the initial upward component of velocity of the frog, the thing we don't have in our known values. We do know the final y component of the frog's velocity relative to its upward trip to the maximum height, which will be 0. We also know the constant acceleration, and we also know the vertical displacement during that time period. So 2 times a, which is negative 9.8 meters per second squared, since we're in free fall, and 2.5 meters was our displacement from ground level up to our maximum height. Negatives cancel. This ends up being 49 underneath the root. Square root of 49 is 7. That means we must have had an initial y component of velocity equal to 7 meters per second. Once we know that initial y component of velocity, and we also know that the final y component of velocity for this upward journey will be 0, then we know that the change in velocity is 0 minus 7, which is negative 7 meters per second during this first going up time period. The constant acceleration for free fall, which anytime you're unsupported and airborne, you're in free fall, is negative 9.8 meters per second squared. 7 over 9.8, negative 7 over negative 9.8, if you prefer, the negatives cancel, is equal to 0.7143 seconds. But they didn't ask us for how long it took the frog to jump up. They asked us for how long it took for the frog to jump up and come back down. If you leave from and return to the same height in free fall, you will spend half of your time going up and half of your time going down. So the total time is just twice this number. All of our inputs had two significant figures, so our output should have two significant figures, and that would be 1.4 seconds. 5, still dealing with this frog. We can keep all of the stuff we learned and knew from the last question. The things we're going to use is that at the maximum height, which we're now going to call an initial time, because we're going to now deal with the time going down rather than going up. We will have a instantaneous velocity of 0 meters per second. So this is still the maximum height, and at the maximum height, you must stop. The y component of acceleration the whole time is still negative g, and the amount of time spent going down is equal to the amount of time spent going up in this situation, and we've already solved for that in the last problem. Once we have this information, we can very easily just use the definition of acceleration, and it's decomposed this way in one of your equations on your quiz and on your exam. And we can simply solve for the final velocity of the downward journey of the frog from the highest point back down to the ground, which will be equal to the initial velocity at the highest point, plus the constant acceleration times the amount of time it spent going downward. Amount of time goes there, acceleration goes there. This is 0. And we'll end up with -7 meters per second. And what you might notice is that is exactly equal to the velocity we started with going up, but in the opposite direction, which is also necessarily the case if you are in a free fall situation and leave from and return back to the same height. Quiz 3. So quiz 3, chapter 3 brought in this concept of 2 dimensions and how that plays with vectors, and the math has to get a little bit trickier because vectors have sizes and directions, and the way you add them graphically makes clear why the math gets complicated. So we start with the graphical analysis. Here's vector B. It is 1, 2, 3 units long, pointing to the right. Here's vector A, which is 1, 2, 3 units long to the right and 1 unit upward. Okay, and the math is going to be 2b minus a. So the way we do this is we first draw 2b, which should be 1, 2, 3, 4, 5, 6 units to the right, because 6 is twice 3. So 1, 2, 3, 4, 5, 6 units right would be 2b. And then minus a should be the exact same length as vector a, but point in the opposite direction, which means it should go over 1, 2, 3 to the left and down 1. Those would be the opposite directions of 1, 2, 3 to the right and up 1. And the way we do vector addition, which is what we've turned this into by making vector minus a, so this is now a vector addition of vector 2b plus negative a, is by taking the first vector, placing it somewhere, and then taking the vector you wish to add to it, in this case negative a, and placing the tail of the second vector onto the tip of the first vector. So this is vector negative a placed onto the tip of vector 2b. It then points in the direction it points, meaning it goes down 1 and to the left 3. And then the result of the vector addition will be whatever vector has its tail placed on the tail of the first vector and its tip touching the tip of the second vector. In this case, that is vector 2. So the correct answer to this question would have been vector 2. Vector 2 is equivalent to 2b minus a. Question 2. We have an equation. It says, let vector c be equal to a plus b. Here's vector a, here's vector b, and we just talked about how you do vector addition. They happen to already be placed in a tip-to-tail arrangement, meaning here's the tail of a, here's the tip of a. Tail of b is already on the tip of a. So we didn't have to do any moving vectors around in our head or redrawing them. They're already drawn the way you would want to do them for a tip-to-tail addition, which means vector c should be the vector that has its tail placed on the tail of the first and its tip positioned at the tip of the second. In this case, it's very easy to see what the y component of vector c would be. Vector c starts at a vertical position of 3 and ends at a vertical position of 2, which means it went down 1 unit, which would be -1 unit being its y component, given that we've labeled our axes in the usual way, where the vertical axis is y and the horizontal axis is x. So -1. Question 3. This is a two-part answer here. We had to give the size of the vector and then the orientation of the vector, where it told us the orientation should be degrees above positive x-axis. So we're told a vector has components of +6 units and +8 units for the x and y components respectively. So then it wants to know what's the size of vector A and what's the orientation of vector A. So the way to do this is draw the components in relation to the vector. The x component is always perpendicular to the y component. I don't care how you draw it, but they have to be 90 degrees from each other. So I chose the conventional way of saying x will be right and y will be up, in which case I have a leg of a triangle that's 6 units, a perpendicular leg of a triangle that's 8 units. The vector itself should be then the hypotenuse of that triangle. Okay? That's always how vectors work with components. So if I want this, I can make use of geometry of the situation to say this is a right triangle. I know 2 legs, a squared plus b squared equals c squared. I'm looking for the c part of that puzzle. So Vector A size will be equal to the square root of ax squared plus ay squared, which is 6 units squared plus 8 units squared, which happens to be 36 plus 64, which will be 100. The square root of 100 is 10. That'll be 10 units. And this happens to be a famous type of triangle, which is in the proportion of 3 to 4 to 5, and that checks out. This is a double of that, so this is 6 to 8 to 10. Okay, the angle. You can find the angle given just what was known. We know that the x component was 6 units, the y component was 8 units. The y component is opposite the angle where they told us to draw the angle, meaning they said, tell me the angle above the positive x-axis. The x-axis goes this way. This angle starts at the x-axis and goes above it. So that is exactly the right theta that those words describe. Relative to where that theta is in our triangle, the y component is opposite. No part of this leg touches that angle, and the x component is adjacent. That angle touches the x component and touches the hypotenuse. So ka toa. Toa tells me opposite over adjacent. Those are the things I have. So therefore, theta is equal to the inverse tangent of the opposite leg, ay, over the adjacent leg, ax, which would then be inverse tangent of 8 over 6, which a calculator should tell you is 53 degrees to two significant figures. Question 4. Soccer ball is kicked with an initial velocity of 30 meters per second. So they don't tell us anything about direction. They just give us the magnitude of the initial velocity. Ball returns to the level surface from which it was kicked. So that's important. The ball starts at the same height that it ends at. That puts a lot of things in play for us. After spending 2.5 seconds airborne, so total time is what we're given. Ball kicked, certain initial velocity, certain amount of time it's in the air. Question then is how far away does it land from where it is kicked? So that would be a horizontal displacement given that the field is level. Okay, how are we going to deal with this? Well, first we're going to write down things we know explicitly and implicitly. Explicitly, we were told the ball was kicked with an initial velocity of 30 meters per second. We were also explicitly told that the ball took 2.5 seconds to leave and return to the ground. Because we know that this is in free fall, it should follow projectile motion, which means the ball should initially rise up, reach a maximum height, and then fall back down. The total time there was 2.5 seconds. Since the ball returns to the level from which it's kicked, we can assume that it will spend half of its time rising and half of its time falling. So the amount of time to rise to the highest point it will ever achieve will be half the total time, which is 1.25 seconds. We implicitly know that. We also know that when we reach that highest point, that we will have a y component of velocity of 0 meters per second at that time. So when we come to the conclusion of the rise period of time, the instantaneous y component of velocity should be 0 meters per second. So that is the only reason we've chosen to pick this out, is because we have useful information about kinematics at that time that's implicit. We also know implicitly, but this should be getting familiar, that anytime you're in free fall, you have a constant negative acceleration of negative g, which is negative 9.8 meters per second squared. These are all the things we know. Some of them were given to us explicitly. Some of them we need to implicitly know. Okay, so what we can do is take the definition of acceleration and use one of our constant acceleration equations and all of this knowledge here of the y component of the object's kinematics to learn something else about the y component of the object's kinematics, and that would be the initial y component of velocity. We don't have that here, but we could get it because we have the final y component of velocity during a period of time, that period of time, and the y component of acceleration during that period of time. So thing I want is the initial velocity. That would then be equal to the final y component of velocity during this time period, minus the constant acceleration during this time period, multiplied by the length of the time period. We did this on purpose. The final y component of velocity during this going up time period will be 0 meters per second. That's the point where you stop and turn around. Minus our constant downward acceleration, so minus negative 9.8 meters per second squared, times 1.25 seconds, which is the amount of time that the ball would have gone up for, tells us that the initial y component of velocity would have been 12.25 meters per second upward. So now we go back to our knowledge of how vectors work. We know we have an initial velocity. We weren't told which way it pointed, but we know its size. We now know what the y component of that initial velocity vector is, 12.25 meters per second, which means we now have two parts of what has to be a right triangle. X component and y component must be included in a right triangle that includes the vector itself. Anytime I have two parts of a right triangle, I can solve for any other part of the right triangle. In this case, we will again use Pythagorean theorem, but we have a hypotenuse and a leg. So to solve for the other leg, it would be hypotenuse squared minus leg squared. Take the square root of that subtraction, would give me the missing leg. So leg, x component, thing I want, equals the square root of the vector itself squared minus the other leg squared. And that will end up being 30 squared minus 12.25 squared is, after you take the square root of it, 27.385 meters per second. That's then the x component of the initial velocity, which is the x component of the velocity for the ball the entire time it is airborne. Because whereas you have a constant acceleration in your y component of motion, you have a constant velocity in the x component of projectile motion. So by finding this, we can apply it to the entire time period, that being this leg. And that ultimately lets us get what we want. We didn't want a vertical displacement, which we were actually given. We wanted to find the horizontal lateral displacement of the object across the full time period. So to get that, we go to our constant velocity equations and we say that the lateral displacement of the ball will be equal to the constant horizontal component of the velocity during this full time period multiplied by the full time period. So that would be 27.385 meters per second times 2.5 seconds is 68.46 meters, which to two significant figures is 68 meters. Finally, question 5. Question 5 is a relative velocity problem. It's a hard one, but there's key concepts that work in any relative velocity problem, including if I give you an easier one that you want to make sure you take note of. In this case, we have house A and B. We are in a boat that's on a river. The river, we are going to presume, has a current of flowing water. And what we're told is the separation of the houses located on land is 2 miles. And then we're told that a boat that's traveling at the same speed relative to the water the entire time takes 5 minutes to get from house A over to house B, but then only 2 minutes to get back to house A from house B when it turns around and keeps that continuous speed relative to the water. And the question then is, based on this information, can you figure out how fast the water is flowing in the river? So, trip 1 from A to B, trip 2 from B to A, I'm just going to define some things here. References in that case are on land. And trip 1 takes longer than trip 2, so we can presume that the water must be flowing to the left, right? So when we go from A to B, we're going against the current. When we go back from B to A, we're going with the current, and that's why we travel faster from B to A than we did from A to B. Notation, I'm going to use L in my subscripts to denote references on land. That's where the houses are. That's where our 2 miles is measured. B is a reference of the boat, and R is a reference of the river. Okay, so what we know is that on trip 1, so velocity of trip 1, which is measured between the boat versus land, right? That's you in the boat traveling versus the land reference points, is equal to the displacement you accomplished relative to land divided by the amount of time in the first trip from A to B. And that would be 2 miles to the right in 5 minutes. We can convert that to miles per hour since we want our answers in miles per hour by taking the fact that 60 minutes equals 1 hour, minutes cancel, and we'll be left with miles per hour, and this will end up being equal to positive 24 miles per hour, or 24 miles per hour to the right, was the boat's velocity relative to land during the first trip. During the second trip, we do it the same way. The displacement measured relative to land was negative 2 miles in this case because we traveled to the left. We did that in 2 minutes, same conversion factor, and we'll find that our velocity during the second trip was negative 60 miles per hour. So we're moving pretty quick. Those are both velocities measured for the boat relative to land. What the question's asking is, what was the velocity of the river relative to land? And the way this works is you can always find the velocity of something relative to something else if you have two additional relative velocities. So the way that works is if I want a velocity of a boat relative to land, then what I'm going to need is a velocity of a boat relative to some common reference plus a velocity of some common reference relative to land. So see how the second subscript matches the second letter in the subscript of the thing I have, and the first subscript of the first term matches the first letter in the subscript of the thing I have. So it goes, first subscript is the first subscript of the first, followed by common, followed by common, followed by second subscript. So you basically make a sandwich where the outer subscripts match what's on the other side. And then you have a common reference that bridges. Anytime you set up a vector equation this way, it will always work. That's the key to doing relative velocity equations. So then we go from vector form to speed, and we say that, okay, we know that the river's flowing to the left, and in the first journey, we know that the boat was traveling right. So the velocity of the boat relative to the river must have been a speed that pointed right, minus the speed of the river, which is the magnitude of this velocity, which must have pointed left. On the second one, we had negative 60 miles per hour. In that case, we were traveling left. So our velocity of the boat relative to the river would have been negative the speed of the boat relative to the river, because speed is the magnitude, negative is the direction, and the river should still be flowing left. So the speed of the river relative to land is still in the negative direction. And what you see is I have two things that are unknown, but they're the same two unknowns in two equations. And anytime I have that, I can solve for either via some form of simultaneous equations. This one happens to be set up perfectly for equation cancellation. That's where you just take one equation and add it to the other. So 24 plus negative 60 is negative 36 miles per hour. VBR minus VBR is 0. That term cancels. That's why the term cancellation, equation cancellation, that's where that comes from. Just by adding the equations, one of my terms just takes care of itself. And minus VRL is minus 2 VRL. And so I'll end up having negative 36 divided by negative 2 is equal to my speed of the river relative to the land, which is 18 miles per hour. And that is your quizzes 1 through 3 key.